Every day, your home fights a war you never see. The sun hammers your roof with roughly 1,000 watts per square meter. That energy passes through your shingles, heats your attic to 150 degrees, and starts cooking the air inside your house. Your air conditioner kicks on, the compressor groans, your electricity meter spins, and your monthly bill climbs past $200, past $300, sometimes past $400 in the summer months. But in 1969, NASA solved this problem. They needed to protect spacecraft from the extreme temperature swings of orbit, 250 degrees on the sun side, negative 250 on the shadow side. The engineers at Marshall Space Flight Center developed a coating embedded with microscopic hollow ceramic spheres. These spheres reflect solar infrared radiation away from the surface instead of absorbing it. The key is something called emissivity. Every surface has an emissivity rating between 0 and 1. A perfect black body absorber has an emissivity of 1. It absorbs everything. A perfect reflector has an emissivity of near 0. It bounces thermal radiation back. Most house paint has an emissivity of about 0.90. That means it absorbs 90% of the infrared energy hitting it, converting it into heat inside your walls. NASA's ceramic coating had an emissivity below 0.25 for solar infrared. That means 75% of the thermal radiation bounced right back into space. Here is the physics. Infrared radiation travels in wavelengths between 780 nanometers and 1 millimeter. The sun's energy peaks around 500 nanometers, visible light, but nearly half of the total solar energy arrives as near-infrared, between 780 and 2,500 nanometers. This is invisible heat radiation. The hollow ceramic microspheres in the coating are typically 30 to 100 microns in diameter. Their curved surfaces create thousands of tiny convex mirrors that scatter incoming infrared photons at random angles. Instead of the photon diving into the wall material and exciting molecules, creating heat, it ricochets back toward the sky. But that is only half the mechanism. The second part involves thermal conductivity. Air trapped inside the hollow microspheres has a thermal conductivity of just 0.025 watts per meter Kelvin. For comparison, solid paint has a conductivity around 0.5 to 1.0. That means each microsphere acts like a tiny thermos bottle, blocking conducted heat from passing through the paint film into the wall substrate. So you get a double barrier. Radiant heat bounces off. Conducted heat gets trapped in microscopic air pockets. The combination reduces heat gain through painted surfaces by up to 40%. Now, here is where the story gets interesting. After the Space Shuttle program ended, this technology became commercially available. Companies started manufacturing the ceramic microspheres at industrial scale. The raw materials, mostly silicon dioxide and aluminum oxide, cost roughly $500 per gallon when mixed into standard exterior latex paint. And the results were dramatic. Tests conducted by Oak Ridge National Laboratory showed that buildings coated with ceramic-infused paint maintained interior temperatures 5 to 10 degrees Fahrenheit cooler than identical buildings with standard paint. In Florida, a test home showed a 21% reduction in cooling energy costs. The Department of Energy published these findings. Independent labs confirmed them. The military started using the coatings on metal roofing at bases in Iraq and Afghanistan, where container housing reached 140 degrees without it. But the air conditioning industry generates $130 billion per year in the United States alone. Carrier, Trane, Lennox, and their distribution networks employ hundreds of thousands of people. The replacement market, where homeowners buy new units every 10 to 15 years at $3,000 to $8,000 per system, depends entirely on one assumption. You need mechanical cooling. When building scientists presented the ceramic coating data to the International Code Council, suggesting it be recommended in building standards for hot climates, the proposal was quietly shelved. No vote, no public explanation. The HVAC industry had 47 registered lobbyists at the ICC meeting. Let me explain exactly how you can make this paint yourself, because the chemical engineering is surprisingly simple. You need 3 ingredients. First, hollow ceramic microspheres. These are sold as cenospheres, a byproduct of coal combustion. You can buy them from industrial suppliers for $2 to $5 per pound. A pound will treat about 2 gallons of paint. Second, you need a high-quality exterior latex paint. Any major brand works. White or light colors are best because they already reflect visible light. The ceramics handle the infrared spectrum that color alone cannot block. Third, a thickening agent. The microspheres reduce the paint's viscosity, making it too runny. A small amount of hydroxyethyl cellulose, available at any paint supply store, restores the consistency. The mixing process matters. You cannot just dump the spheres into the paint. The microspheres are hollow and fragile. If you use a high-speed mixer, they shatter, and you lose the insulating air pockets. Mix slowly with a drill at 300 RPM or less. Fold the spheres in gradually over 10 minutes. The optimal loading is between 30% and 40% by volume. Below 30%, there are not enough spheres to create a continuous reflective barrier. Above 40%, the paint becomes too thick and loses adhesion. Apply it in 2 coats. The first coat creates the adhesion layer. Let it dry for 24 hours. The second coat builds the full reflective barrier. Total film thickness should be 10 to 12 mils, about twice a normal paint job. Now, let me address the skeptics. Some people claim this is just white paint marketing. They are wrong. The difference is measurable and specific. White paint reflects visible light. Wavelengths between 380 and 700 nanometers. But it still absorbs near-infrared. Wavelengths between 700 and 2500 nanometers. That is roughly 50% of the sun's energy. Ceramic microsphere coatings reflect both visible and near-infrared. A standard white house paint might reflect 80% of visible light, but only 20% of near-infrared. A ceramic-loaded white paint reflects 80% of visible and 70% of near-infrared. That additional 50% of near-infrared reflection is the entire game. The difference shows up immediately on an infrared camera. A wall painted with standard white paint glows hot orange on a thermal imager. Surface temperature 160 degrees in direct sun. The same wall with ceramic coating shows cool blue. Surface temperature 115 degrees. That is a 45-degree difference on the exterior surface. Inside, that translates to roughly 8 to 10 degrees less heat gain through the wall assembly. Your AC runs less, your ducts stay cooler. Your whole system operates more efficiently because it is not fighting as much thermal load. And the coating lasts. The ceramic spheres are inorganic mineral material. They do not break down under UV exposure like organic paint additives. Buildings coated with ceramic paint 15 years ago still show the same performance numbers. The spheres do not fade, chalking, or degrade. Several countries have already mandated reflective roof coatings. California's Title 24 Energy Code requires cool roofs on commercial buildings. India's Ahmedabad Heat Action Plan distributes reflective roof coatings to slum neighborhoods, reducing indoor temperatures by 5 degrees Celsius. Programs in Mexico, Colombia, and Morocco have documented 20% to 30% reductions in cooling energy. But extending these requirements to wall paint, where the 5 per gallon ceramic additive would save homeowners $50 to $150 per month on cooling bills, remains under study. The air conditioning industry prefers that you buy a new $8,000 unit every 12 years instead. The physics is proven, the materials are cheap, the application is simple. NASA figured it out in 1969. Oak Ridge confirmed it. The U.S. military uses it. But 55 years later, your house paint still absorbs 90% of the sun's heat, and your AC still runs 8 hours a day. $5 of ceramic powder per gallon of paint. That is the cost of a reflective barrier that can cut your cooling bill by 20 to 40%. The science has been public since 1969. The question is not whether it works. The question is why this is not in every can of paint sold in America.